Hello everyone. Today I'd like to talk about different kind of popular data set. Form of data set that you will see nowadays. You will see a lot. They talk about supervised data or unsupervised data set. So whenever you train the machine with a well-labeled data set, we call that supervised learning. And whenever machine learns from unlabeled data, we call that unsupervised learning. If you learn about this kind of things more, you will think dealing with a labeled data set is easier, it's better, especially statisticians always used to use labeled data set. You always think, okay, this is very easier to deal with labeled data set, but actually in reality unlabeled data are really helpful when machine wants to perform a kind of more complex tasks. So unlabeled data are very beneficial, very helpful. Okay, so now supervised data help you to produce outcomes based on the previous experience, which is a kind of Bayesian approach. Mainly you can solve real world problems with supervised data set. On the other hand, unsupervised data help you to explore unknown pattern, and it's useful for categorizing the data set. Okay, so if you like to, for example, if you like to create an algorithm to drive from one place to another place, you can use some information like weather conditions, construction location, or let's say traffic information, time of commuting, this kind of things. And as we know, all of these are kind of labeled data. Means if we have in our data set, if we have a column, it says weather condition or construction location, means we know about this column of data set, right? So this is a labeled data set. So and you give, imagine you give this information to machine as an input, and then you get the output that is kind of a prediction. For example, prediction of what? Prediction of the time you must leave to be able to arrive to a certain location on time, or many other outcome that you're interested in. So this is a kind of example of supervised data set. You have a labeled data set, you give it to the machine as an input, and then you will get an output and predict the result, right? So how model can predict the commute time? So what it does, it looks at the relation between the variables we gave to the machine, like weather condition or construction location and other variables it stores in itself. And then this knowledge will help the machine to predict the future outcome. So this is a supervised learning, right? So for example, machine will see that during a certain time of the day, going from one place to another place takes time, for example. Or machine will see during the time winter, or whenever weather is cold, it's more difficult to be on time. So these are all the information machine will gather and use this information to predict the accurate outcome. Okay, so this is an example of supervised learning, right? We have a labeled data, machine will store the information, and then will use this knowledge to predict the outcome. Okay, so what is the example of unsupervised data set? So whenever, for example, you are giving an information of a doll, for example, to computer. Then later if you give a similar information to the machine will compare this information with the information that received in the past, and then we'll compare these two information and we'll see how similar these two informations are, right? And if the new information is similar to the previous information, machine will says, okay, this is the doll, because the features are more similar, right? So this is actually the easiest example. When I said doll, the easiest examples are the pictures, images. When for cancer, for example, they are comparing different images to the images of cancer kind of organ. So these are kind of very useful, especially in kind of detecting the disease. Okay, so imagine in this example, unsupervised data, right? Imagine if machine already knew this new object is a doll, right? So this wouldn't be an unsupervised data anymore, right? Because machine already knows what is this new information. So when machine knows what is this new information, this will be the example of supervised data. So as long as machine doesn't know what is this new information, we can call this unsupervised learning. Okay, so now there are techniques to work with unsupervised data or supervised data. So for supervised learning, we use some techniques like regression, classification. And then classification itself, we already saw regression, talked about regression. So classification means to group the output inside a class. And then we have different classification actually. And for unsupervised data, the techniques are like clustering and association problems, and I'm more familiar to clustering. I worked with clustering more. Okay, so what clustering does, it deals with finding a structure or pattern in a collection of uncategorized data. Okay, so today I have the a gene expression data that I'm going to use for this lecture. So this gene expression data that I got it from this website, and I'm going to upload it for you. This data has some columns that are samples, and then it has some rows that are the gene name. So let me import NumPy and pandas to show you how the data look like. And then I'm going to upload two paths to my computer, to my directory, and then I'm going to call one of them gene information, and pd.read underline CSV. This is for path 2. Let me first show you this one. This is the data set that has gene information, and then the other one is gene expression exp, and I'm going to call this original because I'm going to change this later. pd.read underscore CSV. This is for path 1, and then look how the data look like. and then I will relate these two together. So look at this star, means still it's loading. So whenever you see a star, give it time, because the data set is very big, so it's taking time. Okay, so as I mentioned, the gene expression data set has some columns that are the sample's name. These are some information of sample. For example, these are the information of embryo, human embryo. And then TRI says this is a method that they got the kind of transcript extracted. HV is a sample name, some method. Day 10 means this is an embryo at day 10, and then this is a kind of method. And this one says this is an embryo 1, for example. B1 says batch 1, and 1 says this is a sample 1. So these are the information. You can get all of these after studying the data on this website. You will understand what this means, but you don't have to. So just know that this is sample 1, sample 2, sample 3, and I have like 96 samples in this data set. Imagine 96 columns, right? And then what are these rows? These rows are all the gene symbol, gene name. We have like 19,000 here. Look at this. Actually, this data set actually has 545 columns. Oh, okay, I'm showing you this one. Good, okay, that's fine. So look how many columns we have here. And then I wish I could remove this one. Okay, so here I'm going to show again. Okay, so here 2,545 columns, which are samples, right? And then the rows are genes name. Let me comment this here. Rows are genes name, or we call that symbol. And then this one column, this many columns are the samples. Okay. So imagine what a huge data set is that, right? And imagine if I want to draw a scatter plot of this, or I want to, for example, show this data like just for 2-3 samples and all the gene. So how many dimensions my plot would have? Because imagine if I show this on x-axis and this one on y-axis. Wow, there would be many kind of dimension for a data set, for a plot that is able to, you know, show this huge data set. So it will be a lot. Okay, so now okay, let me explain it in an easier way. So imagine these are people's name, for example, and this is person's height, this is person's weight, this is person's let's say what is the other attribute of a person? Can be numerical, whatever attribute. Look, all of these, just imagine these are the characteristics of people, right? If I had just height and weight, I could show this on x-axis and I could show weight on the y-axis, right? 2 dimension for my plot, correct? What if I have the third attribute I want to show while I'm showing height and weight? So it will be 3 attributes, and this is going to go on z-axis, for example. So we will have 3 dimensions for our plot, right? And then imagine here there is one more, another dimension, 4 dimension, 5 dimensions. So I would have like 2,545 dimensions if this gene name were people's name and all these columns were people's attribute. So imagine that way. If this data set is difficult for you to understand, just I'm comparing it with a really easy data set. So conclusion, this kind of high dimensional data set is very difficult to visualize and understand. So in order to understand this high dimensional data set, we must use some easier method to kind of reduce the dimension, right? Just keep those attributes or characteristics that is more important to explain the person's characteristic, right? We can just choose some of the characteristics that are very important. So in this data set also we can choose those samples that are explaining these genes very better. For example, look at this. This sample has lots of zero in there. Means these genes didn't have any transcript information in this specific sample. This gene also didn't have. Just some of the genes has, right? So we are going to choose those samples that are explaining the data set in a better way. So this is the aim of classification, for example, or this is kind of aim of dealing with high dimensional data, to reduce the dimension, to be able to explain the data set in a better way. Okay, so for this kind of data set, actually I didn't explain about this. So what is this? So in this gene information, we will see in each row there is some information. This column says this is the sample's name, and also this is also sample's name, both of them. And then this one says original, this one says date, this one says IVC. Well, you know what? I have to edit the data and show it again. Okay, now it's better. So we have just one column sample and this looks much better. Okay, so look what it says. The first column shows the sample's name, and then for this sample's name it shows the type of this sample, and then the original, and then the day this sample shows the embryo, the day of embryo, and then this is IVC. This is in vitro actually compartment, I guess. And then this is the embryo name. This is the first embryo, and as you see there is embryo 7, and then different name of batch and all the other information. I even here also will see this gender of embryo, and then this one is actually the cell, which is kind of 3 different type of cell. Okay, so you don't need this kind of information. I'm just explaining the data set, because later when I use this one and apply it to this data set, you will understand what happens. So each of these sample is one column here, right? So for each of column we have more information, as you see. So most of gene expression data set has this kind of setup. One data set shows all the information of sample, another data set shows the gene and samples and the gene expression for each gene in each sample. Okay, so now what we want to do today with this data set, we want to talk about PCA, which is a type of clustering. They call that principal component analysis, and it's a very kind of popular analysis, and it's very useful in high dimensionality kind of data set. They reduce the dimension of data set with PCA analysis, and they will analyze the data set, create clusters, and they compare, for example, samples to see what characters or features are more similar and more important to keep. Okay, so Then PCA is a dimensionality reduction method and is often used to reduce the dimensionality of a huge data set like gene expression data set. And what we do by transforming a large set of variables into a smaller one that still has most of the characteristic or information of the individuals in our sample. So PCA used to transform high dimensional data set into a data set with fewer variables. So for example, we get this data set and transform it to a data set with a lower number of samples. Instead of 2,500 samples, we just choose those samples that are explaining the genes in a better way. Okay, so the resulting variables, again, the resulting variable will explain the maximum variance within the data set. So the most kind of focus, the main kind of aim is to get those variables that explain the most of variability of the data set. So PCA actually is used prior to unsupervised or supervised machine learning. So we can use it for unsupervised and supervised data set. Doesn't matter. So for this reason, you will see here, I still have the column's name, right? Still the data set is labeled for us. So I can use it as a kind of for supervised learning, right? So PCA is used for either of them. So the most important use of PCA is to represent a kind of multivariate data table as a smaller set of the variables in order to observe some trend or clusters or even outliers, because we can even use PCA to remove outliers from our data set. Because imagine if I kind of eliminate those samples that has lots of zero transcript, so those samples were outlier, right? Those samples were not similar to other samples. Those samples didn't explain that much. So those samples would be an outlier. Okay, so principal component, again, is a technique to use to emphasize variation, and it brings out the most strong pattern of the data set. Okay, so what we do to start with our analysis, we are going to use two packages. Actually, the main package that we are using is sklearn. You remember, from sklearn. Now I'm going to get this attribute, decomposition. We are going to import PCA from decomposition in sklearn. And then again, another one will be from sklearn dot pre-processing. We are importing standard sklearn. Okay, so this package is for PCA, right? This package is this second one. This package is used to standardize the data set. So it's always better to standardize our data set if you have high dimensional data set, because some of, for example, this sample maybe are in different scale, or other sample different scale. So we always should standardize them And one thing that I always were kind of confused years ago, and I studied this a lot to understand what's going on. There are two vocabulary you will see a lot in statistics: normalization, standardizing data. So what that means by normalization, what that means by a standardized data set. So when we standardize data set, we are rescaling the distribution of values. We are rescaling the distribution of values. So we are going to set up a mean for the distribution and a standard deviation for the distribution, and standardize all the data set to have the same distribution. So most of the time we are standardizing the data set to have a mean of 0 and a standard deviation of 1. So what that means, we are going to set up the center of data set to 0, and then the standard deviation will be 1 unit on the right side of mean, 1 unit on the left side of the mean. So the formula for that, the simplest formula for standardizing data is subtracting each value. For example, this one, subtracting this from the mean of data set and then dividing by the standard deviation of data set. You can do that inside each sample, or you can do that to whole data set to standardize the whole value based on the mean 0 and a standard deviation of 1. Okay, so this was standardizing data, rescaling the distribution of values. So now normalizing data is rescaling the data from the original range. So we want to know what's the maximum minimum of data, right? What is the range? Range means you know the minimum of value in the data set, you know the maximum. And then what normalization do, it will rescale the data from the original range to the new range. And what is the new range? New range is from 0 to 1. So this is a difference between normalizing data and standardizing data, remember. So I will write this here, and normalization versus standardizing data. Okay, so for this lecture, I want you to look this up and study this more and find out more information about these two. What is the differences between these two, and learn about this more, and write down for me one paragraph about what you learned, what you learned that I didn't mention, and also just explore the internet and see what they are talking about, the difference between normalization and standardizing data set. Okay, so this will be your participation point. Okay, so it's very better to standardize the data set, especially gene data set. So we will rescale the whole data set to have a mean of 0, standard. Okay, so let me write it down here. Standardizing the values in the data set to actually data set with mean equal equals 0 and variance equal 1. Okay, so what we do to do this, we are going to use a standard scalar. We saw this here, right? Dot, and then we are going to feed transform. And then what is our data set? Gene expression. Oh, actually, one step before this. So what we are going to do, we are going to just keep all the values, right? This column has the information that are all the name, right? Name of genes. And if I apply the transformation and standardizing the data set on this data set right now, it's going to give me an error because I have a string here and the data set is not just value. So here I'm going to add a step to remove the first column, which is the gene name, because if we don't do this, it will cause error for standard. Okay, good. So how we do this? This was my original data set, right? I'm going to create a new data set without new one, like I don't want to mention the actually I want to create a new one. Okay, so what I do, I'm going to drop. So drop. So using drop, remember you can drop one of the column, what is that, row, or as many column and row you want. Original dot columns, and I'm going to remove the first column which has index 0, axis equal 1, in place equal true. In place equal true, it says do this and change the original data set right away. Let's see what happens. Yeah, where is that? Oh, still it's loading. Okay, good. So we got rid of those, the first column, those names, right? Okay, so now let's just show 3 of them. This one also, let's show 3 of them. This is okay, good. Okay, so let's continue here. I'm going to change the name of data set here when I'm standardizing the data. I'm going to change the name of data set, and then I'm transforming the original data set, right? And then let's print this and see what we get when we standardize the data set. What happened? Oh, I wrote down in a raw data set. Let me change it to code. Okay, good. So now let's see. Look at the values. Now values are way more similar, and they are standardized, right? In compared to the previous values I had. One was 38, one 0. Do you see that? Okay, so now we have this. So I'm going to actually comment this out because I'm going to continue doing something. So I'm going to change this gene expression data set that I created to data frame. Do you remember? We can create a data frame and we can say columns of this new data frame. Look at this. Here I am using the columns of the previous data set to assign it to the new data set. So how do I do that? The previous data set was gene expression original, right? And then if I say columns, it's going to get the columns of the original data set and say now column of new data set is equal to column of the previous data set. Let's see what happens. Let's print it. Okay, so now we have the standardized data with an appropriate title for each of the columns. Okay, so now what we did, we standardized our data. Now the next step, we are going to perform PCA. Okay, I'm going to write down PCA equal to, as you know, we already used this, right? We already imported this, right? I'm going to use the imported PCA and then I'm going to fit the data set. And then, no. And I'm going to show you what this gives us. So this gives us component variance. Oh, sorry, I just created empty one. Okay, now to create the component variance, I'm going to say explained underline variance underline ratio, and then another underline. I found this notation so strange. I don't know why they do that. Here, in this way, what we are doing, we get component variance. And then in parentheses, proportion of variance. Okay. So for each of these samples, it's going to give us the proportion of variance. And then what other thing we can get? We can get the eigen values and then we are going to talk about all these eigenvalues and everything. So let me print this. Whenever we are using that to graph them, you will see how these are beneficial. Okay, so I'm going to get explained variance, and this time these are not ratio, these are just the eigenvalues. And let me create a gap and print them in next line. And then one most important thing that we should always look when we are using principal component is cumulative proportion of variance. So I'm going to use this because actually I'm going to use NumPy. So I'm going to create a cumulative sum variable, and then using NumPy cumulative sum, is that correct? Cumulative sum, and I'm going to create a cumulative sum of the explained variance ratio, and then I'm going to print the cumulative sum to show you what this shows exactly. Okay, so what I did doesn't explain variance ratio. Okay, look at this. I forgot this one. Okay, so now it will show the cumulative proportion of variance. So what this does, I'm waiting for the, okay, see what this does. This will show the proportion of variance, this especially shows the proportion of variance that PC1 explains. This shows the proportion of variance that PC2 explains, and for all the PCs, right? And it's always like that. The first PCs will show the highest variability. And then look at this. We have multiplied e power negative 0.1. Means this one is 0.7 something. When I say 0.7 something means it's 70% of the variance, right? And this one shows 0.8, means 8% of the variance. And then this one shows 7%. So the first one shows 70% of variance, then 8%, then 7%. Pay attention to this negative power negative 0.2 or 0.1. And then in order, it's going to show the PCs that shows the less kind of proportion of variance in the data set. So this cumulative is easier to understand. It says the first PC shows 70% of the variance. And then if we have first PC and then second PC up to, we are explaining up to 78% of the variance in the data set. And then PC 1, 2, 3 all together up to 86% of the variance in the data set, right? So now I will show you only the first important PC. Let's say 0 to 7 shows PC 1 to PC 6. Let's see what happens. So it shows the first important principal components that explain about this data set. And look, PC 1, PC 2, PC 3, PC 4, PC 5, 6, and 7, right? All these up to PC 7 will explain 90% of the data set, 90% of the variability in data set. Normally, when we are talking about principal components, we choose principal components up to like, let's say, the first 2 or first 3 or first 4 principal components. If we get those principal components that explain 75% of the data set, that's amazing. That's really good. but we can always get more principal component. But sometimes getting more principal component actually will bring down the quality of data set. Remember what we wanted to do, we wanted to reduce the dimension and choose those characteristics that explains more about data set, right? Just having two of them, two principal component, can show the characteristic of genes on 2 dimensions, right? And then 3 of them, let's say 3 dimensions. What we can do and what we will do in principal component, we will get this characteristic and show this characteristic versus another characteristic, for example. Or we get principal component 1, we show principal component 1 versus principal component 3. And we will see how showing this characteristic against each other will classify and will cluster our data set in a better way. And that is the most aim. How this principal component can explain the data set in a best way and cluster our data set to know exactly what features are kind of bold and important in our data set. Okay, so we'll continue talking about principal component in the next lecture.